Hello, everybody. So today we're doing assignment 8, functions and reference graphs. There's a bunch of stuff here for us. I actually want to start with functions, and I know you've been talking about functions since middle school, uh, but there are some things about functions that still confuse students, and I'd like to dig into that a little bit today. So first, let's talk about uh, when I think about a function, I know it's a relation whose graph passes the vertical line test. I know if I look at a table, each input goes to only one output. Um, but I actually want to focus on the language. So height is a function of time. So this is the dependent variable because it depends on, is a function of this independent variable. Okay, and so, I'll see h of t. I bring this up because I want you to um, write the area of a circle as a function of radius. Well, that should be pretty easy, huh? Area as a function of radius is simply pi r squared. But what if instead I say to write area as a function of circumference? Well, that's a little more interesting, isn't it? I'm looking for area as a function of circumference. I know area is a function of radius. I know circumference is 2 pi r. And so what I'm going to have to do is find a bridge between what I know and what I want. So this area formula has radius in it, and I see an r here. If I divide both sides by 2 pi, I can get r by itself, and then I can take this and replace it in here. So pi c over 2 pi squared. So pi c squared over 4 pi squared. We can cancel a pi there. And so r, area as a function of circumference, then, is, as a function of circumference. Area is the output, circumference is the input, is going to be c squared over 4 pi. That's the area of a circle as a function of circumference. I plug a circumference in, I get an area out. How did I do that? Remember, I started with the area formula that I know for a circle, and this other relationship involving circumference, and I did a substitution here. Okay? All right, so how about this one? Area of a square as a function of side length. Well, again, that's pretty straightforward. Area of a square, area as a function of side length, is just side length squared. We know if we have a square whose sides are s, this area is simply side squared. But then what if instead I say area as a function of perimeter? Well, I know the perimeter here is 4s, but I'm trying to get area not as a function of side length, but as a function of perimeter. So I really need to take this helping equation and solve it for s so that I can replace s in this area function that I know with some perimeter stuff. So area in terms of perimeter will be p over 4 squared, or perimeter squared over 16. Okay? All right, how about this one? Area of an isosceles, oh no, let's go with equilateral. Equilateral triangle as a function of side length. So what do we know about an equilateral triangle? Well, we know all the sides are equal. We know that the altitude cuts this side into two equal pieces and is a right angle. Speaking of angles, because the three sides are the same, we know all these angles are the same. And so what I'm looking at here is a 30, 60, 90. What do we know about the ratio of sides in a 30, 60, 90? Well, if this is S, then this is 1/2 S, and this is root 3 times 1/2 S, or root 3 over 2 S. Now, if you didn't remember your 30, 60, 90 shortcuts, what could you do? Well, I guess I could go like this and use the Pythagorean theorem. I could say, well, I know that this is half of the side length because I cut it in half with this, and I don't know what that length is, so side squared equals 1/2 side squared plus question mark squared. So side squared equals 1/4 side squared plus question mark squared. And if I subtract 1/4 of a side squared from one side squared, I'll have 3/4 side squared equals question mark squared. When I come back now and take the square root of both sides to get question mark by itself, I see that I have square root of 3 over the square root of 4, and the square root of s squared is s. So there's my missing side, root 3 over 2s. Whether I use my 30, 60, 90 shortcuts or the Pythagorean theorem, I can generate that helping equation, because now when I think about area of a triangle and I think about 1/2 base times height, but I want area as a function of side length, I know that the base is a side length, and I know that the height is root 3 over 2s. So we're going to have root 3 over 4s squared. Now, I want to say something to you that you're going to probably ignore and be horrified with, but really, at this point in time, I would find a page in your notebook that you can always find where you write down formulas that you've forgotten, but College Board is going to expect that you remember. This, for example, is one of those formulas. The area of an equilateral triangle as a function of side length. This comes up. They actually expect you to know this. So you might want to write this formula down on a page that you're going to call Formulas I'm Supposed to Remember, and make sure that you keep adding to that as you get new formulas. Okay, so we did a little work writing something as a function of something else. We did some conversions in that, and I think that was pretty useful. Right. One other thing I want to say, when I see height as a function of time, I just want to sort of reinforce, from an English language perspective, this word is the output. This word is the input. Because if I have something like donuts, as a function of carrots, that's a little less obvious that, oh, I'm talking about h of t here. No, first word is my output. It depends on carrots, so I want donuts as a function of carrots. Okay? So when in doubt, use your language skills to know that this word is the output, the dependent variable, and this word is the input, the independent variable. Okay. Next, I want to come back and review domain, because not only does domain come up a lot this year, but in fact, interval notation pervades so much of what we do. And whenever we write domain, we remember that it has to be in interval notation. So hopefully you remember that domain for all polynomials is all real numbers, or negative infinity to infinity. That's for any polynomial, and we deal with lots of polynomial functions. Okay, but what about things with restricted domains? Well, we remember two main things that restrict domains. One is no negatives under an even index radical. So no negatives under square root or fourth root or hundredth root. It's okay to have a negative under a cube root. That's not a problem. It's the even index ones where we have a problem. And what do we do in this situation when we have even index radicals? We set the radicand, which is the stuff under the radical sign. And oh my God, I would so much prefer to say radicand than have to say all those words. So I want to set the radicand greater than or equal to 0. That's our first type of restriction. Our second is zeros can't be in denominators. Right? So 1 over whatever you want, but not 0. So that denominator can't be equal to 0. Okay? So those are our two big ones. And of course, we'll think about other domain restrictions, like when we have vertical asymptotes showing up in log functions, or things like tangent, cotangent, secant, and cosecant. Those we'll touch on as well at another time. I want to go back now and just look at finding these domains. Okay, so I'm going to set the radicand greater than or equal to 0. X is greater than or equal to 3. That's great. No, don't give me this inequality notation. I need interval notation. Remember, x greater than or equal to 3 means x can equal 3 and be all these numbers bigger than 3. And so interval notation is just a way to describe this visual understanding that I see. We're going to start at 3. We always start with the smaller of the two boundaries, and we're going to go forever. Remember that infinity always gets a parenthesis. Okay? All right. So now I'd actually like you to try these next problems. So I'm going to write down a problem, and I'm going to ask you to pause the video and tell me what the domain is. Okay, so find the domain of this, pause the video, do it, come back, and we'll compare answers. Okay, welcome back. So I'm setting the radicand greater than or equal to 0. I'm adding x, and I see that x is less than or equal to 3. Here's 3, could be equal to, but x is also less than. So negative infinity to 3, and because 3 is included, I use a bracket. Now, I'm a little concerned that some of you might have done this. where you subtracted 3 from both sides and divided by -1 and came up with x is greater than or equal to 3. Hey, that's not what I have. So what did this student forget? They forgot that whenever you multiply or divide both sides of an inequality by a negative, you have to flip the inequality sign. And that's why I would rather move a negative x to turn it into a positive x like I did here, than solve for x by getting x alone by first removing this and then dividing by that, okay? So be wary of that. Okay, so let's do a couple more of these. How about y equals square root x squared minus 5x plus 6? Okay, pause the video, find the domain. Okay, welcome back. So I know that x squared minus 5x plus 6 has to be greater than or equal to 0. And I know that this factors as x minus 2 times x minus 3. And so I get critical numbers at 2 and 3. And then I'm going to test these intervals. So I'm going to plug in something over here, like 0, like 2.5, and 4. And I'm going to plug them into this inequality and see what I get. So if I plug in a 0, I have a -2 times a -3, which is a positive 6, and that is greater than or equal to 0. So this is a yes. If I plug in 2.5, 2.5 minus 2 is 1/2, and 2.5 minus 3 is -1/2, and so that's -1/4. Is -1/4 greater than or equal to 0? No, it is not. And then finally I plug in a 4. 4 minus 2 is 2, 4 minus 3 is 1, 2 times 1 is 2, and that is greater than 0. So these are my intervals, and so I end up with -infinity to 2, union 3 to infinity. You could, also think about this testing graphically. We've got a parabola. It points up. So here's that parabola. And we're asking, when is the parabola above or intersecting the x-axis? Well, for all these x values and for all these x values. And we've got that. This graphical approach is easier with polynomials. Once I get to rational functions, it's a little more problematic. Hey, I wanted to say one thing about this. Some people do this with this problem. And then they say x is greater than or equal to 2, and x is greater than or equal to 3. And so they say 2, closed circle goes this way, 3, closed circle goes this way. And then they either say this and this, but that would be bad because there's overlapping here, or they just claim the overlap. Either way, this is horrible. Because, look, this is part of our answer. This is not part of our answer. This doesn't generate the correct answer. So please don't do this problem with inequalities. Do it like we learned in pre-cal, where we change the inequality symbol to an equal sign so that we can find some critical numbers, and we'll put those critical numbers on a number line and test the intervals. That's the way you're going to be sure. Using those inequalities all the way throughout will most likely get you the wrong answer. So don't do that. Okay, so let's go do some more. How about y equals square root 25 minus x squared? Here, you can have some redemption now. Remember, you're supposed to be figuring this out and then coming back. Okay, welcome back. I set the radicand greater than or equal to 0. I'm going to turn that into an equal sign and find some critical points. Hey, remember when you take the square root of both sides, you need to remember the plus and minus. So we've got a -5 and a +5. And I'm going to test these intervals with this inequality. So -6, 0, +6. 6 squared is 36. 25 minus 36, is that greater than or equal to 0? No. How about 0? 0 squared is 0. 25 minus 0 is 25. 25 is greater. And then what about -6? Well, -6 times -6 is still 36, and so I'm still going to get a negative number over here, and so this is no. And so my domain here would be -5 to 5. By the way, don't fall into this trap. Some students report this is the answer because they used their test values. No, you have to use the critical values that you found. That's why we found the critical values. Those are our boundaries, okay? All right. Well, I hope this is feeling pretty comfortable. How about this last radical problem? Cube root of 4 minus x squared, okay? Well, I hope that you saw this was a trick question. You know the cube root function does not have a restricted domain, so our domain here is -infinity to infinity. Pay attention, only even index radicals have a restricted domain, not odd index ones. Okay, so let's take it a step further, and now let's say these 1 over x plus 3. Well, I know I can't have a 0 there. So x plus 3 can't be equal to 0, which means that x can't be equal to -3. On my number line, here's my -3, and I can't be that. That's what I can't be. I can be absolutely everything else. And so I'm going to have -infinity to -3, bracket or parenthesis. Can't be equal to, so it's got to be a parenthesis. Union -3 to infinity. Okay? All right, so why don't you try this one? Y equals 1 over 2x plus 1. Pause the video, give it a try, come back if you have questions or when you're ready to check. Okay, so I'm setting what's in the denominator not equal to 0. And I get x can't be -1/2. On my number line, -1/2, I can't be that, but it can be these, and it can be these. So -infinity to -1/2, union -1/2 to infinity. Pretty straightforward. So let's try something more pre-Cali, like 1 over x squared plus 5x minus 6. Why don't you try this one now? Welcome back. So I know that I have to set that stuff in the denominator not equal to 0. And I can factor here x minus 1, x plus 6. Watch out for factoring. I hope you didn't have 2 and 3 here. So we've got x can't equal 1, and x can't equal -6. So here's what I see a lot of students doing. They do this. -infinity to 1, union -6 to infinity. And that's wrong. So let's put these on a number line. -6 and 1. These are the things that don't work. And this works, and this works, and in here works too. So I need 3 intervals. I need -infinity to -6, I need -6 to 1, and I need 1 to infinity. Okie doke? So now that I've reminded you of that, perhaps you could take a look at this one. Y equals x over x squared minus 5x plus 6. Please find the domain here. Give this one a try. Come back when you're done. Hey, welcome back. So x squared minus 5x plus 6 can't equal 0, which means x minus 2 times x minus 3 can't equal 0, which means x can't equal 2 and x can't equal 3. On my number line, this is what I can't equal. I can be all these other things. This middle section is the most common mistake for students. They completely forget about this. Please don't. So we've got negative infinity up to 2, union 2 to 3, union 3 to infinity as our domain. Okay? How about this one? What if we consider a hybrid? Y equals 1 over square root of x minus 3. Well, I know that I've got here stuff under a radical, but I also know I've got stuff in a denominator. So this thing under the radical says can be equal to 0, but this one says no, you can't be equal to 0. And I'm wondering how I'm supposed to resolve that conflict. Well, let's put this on a number line and test the intervals with, say, 0 and 4. But let's also test this point itself, 3. So if I plug in a 0, 0 minus 3 is negative 3. Square root of negative 3, no, I don't think so. What if I plug in a 3 itself? 3 minus 3 is 0. Square root of 0 is 0. That's okay. But 1 over 0 is not okay. So that's a no. And then if I plug in a 4, 4 minus 3 is 1. Square root of 1 is 1. 1 over 1 is 1. And that's okie doke. So our domain is always going to be the most restrictive. And so I have to combine these two domain restrictions to be x minus 3 is greater than 0. Not equal to anymore because this one can't be equal to. So my domain, parentheses, don't use the 4, use the critical number, 3 to infinity. Okay? So why don't you try this one? We'll do 2 more of these and then we'll move on to reference graphs. Y equals 1 over square root of x squared minus 5x minus 6. Okay? All right, welcome back. So we know that x squared minus 5x minus 6 has to be greater than or equal to 0 because of the radical, but because of the denominator, we know that square root of x squared minus 5x minus 6 can't equal 0. Well, this is saying it can, and this is saying it can't, and we learned in the last problem that most restrictive is what we're going to do. So I've got x minus 6, x plus 1, greater than 0. Please do not do x is greater than or equal to greater than 6 and x is greater than negative 1, because that will be wrong. Instead, put the critical numbers negative 1 and 6 on a number line and test the intervals. If I plug in a 0, I get negative 6 times 1, which is negative 6. That is not bigger than 0. If I plug in something like 10, I have a positive, positive times positive is bigger than 0. And if I plug in a negative 2, I've got negative 8 times negative 1, and that is not, negative times negative, that is greater than 0. So our answer here, our domain here rather, has 2 intervals. It's negative infinity to negative 1, parenthesis because not equal to, union 6 to infinity. Now, I notice that there are a bunch of details in these problems, right? There's the details of factoring properly. There's the details of checking, actually checking, not being lulled into these inequalities. We have to be thinking. And I'll say one of the things that makes this class different from most of your other math classes is we spend a lot more time thinking. This is a class for thinking. Thinking, thinking, thinking. Thinking is not something to be run away from. thinking is something to be embraced. You will have fewer homework problems this year, many fewer homework problems, but you will have a lot of thinking to do, okay? And that will get you ready for college, even if this is your last math class ever. College, you're going to be doing a lot of thinking. I want you starting now. Okay, our last one. Y equals square root of x minus 1 over x minus 4. All right, give that domain a try, and we'll move on from there. Okay, so we know that x minus 1 has to be greater than or equal to 0 because I can't have negatives under my radical. And I also know x minus 4 can't equal 0. So I know x is going to be greater than or equal to 1, and x cannot equal 4. Here's 1, here's 4, cannot equal 4, can be equal to 1, can be greater than 1. Mr. Kukla, what happens at 4? Well, let's test and see. What happens if you plug a 4 in? Square root of 3, no problem, but 4 minus 4 is 0. I can't have root 3 over 0. That's undefined. So even though this is saying greater than 1, and 4 is greater than 1, that hole does not get filled in. Remember, with domain, it's the most restricted case. So our domain will be 1 to 4, union 4 to infinity. Okie doke. Okie doke. Now, let's talk about our reference graphs. Yes, I swear to you, transformational graphing is terribly important. You need to be so comfortable that when you see y equals negative 2, 3x plus 5 squared minus 7, that you can see that in your head, you can discuss the transformations. Oh, look, I flipped it upside down and moved it down 7. Oh, look, I moved it left and compressed it by a factor of 3. And don't worry, we'll come back and talk about these transformations in the next video. But remember, the heart of transformations is actually knowing your reference graphs. So let's start with reference graphs. Y equals x has the reference points negative 1, 1, negative 1, negative 1, 0, 0, and 1, 1. Please remember to label the points on your graph, not off to the side. I will mark the problem wrong if you have the points off to the side and not on the graph. The points need to be on the graph. The points need to be on the graph. The points need to be on the graph. Please label the points on your graph. If you don't do that, you will not get any credit. Great. Next, y equals absolute x. Well, remember, absolute x won't abide by negatives. It turns anything you plug in there into a positive. So all of these are going to flip up. And now we're going to end up with this shape. That's still this with 0, 0, and 1, 1. But this part here reflects up and becomes negative 1, 1. So our reference points, negative 1, positive 1, 0, 0, 1, 1. Please make sure you memorize your reference graphs. But wait, there's more. We've got y equals this. What's that? Well, that's a step function. That's our greatest integer function, also known as the rounding down function. It starts at 0 and goes over 1, and then it goes up 1, and then it goes over 1, and then up 1, and over 1, and it goes down and back as well. Forever. Now, I don't have any reference points for you here, and I can apply the transformations. You know, if I see this, I know that's simply going to take this graph and move it 2 places over. So this point will come over here, and this point will come over here, and this point will come, oops, I skipped 1, or we're moving 2. That's it, we're moving 2. So this will move 2 points over. So we'll have this here and that. And so I can still apply transformations. I'm just not going to be looking for reference points here. I'm going to be looking for this sketch. I have seen int x show up on the AP exam, so please make sure you're comfortable with it. Okay, what's next? How about y equals x squared? This one has the same reference points as absolute value of x, and because of that, it reminds me that not only do I have to know the points, but I also have to know the shape through those points. I'd like to see a nice concave up curve here with the points negative 1, 1, 1, 1, and 0, 0. Okay. Next, how about this polynomial, y equals x to the third? Well, this one has the same reference points as y equals x, but again, it has a different shape. Its shape, concave up over here, and concave down over here. And it would be good if that were a 0 slope. What do I mean by 0 slope? I mean a flat space, concave up, concave down. Just flat at 0, but it's flat there. It's not like the tangent curve, where that inflection point on the tangent curve, I believe, has a slope of 1. We need a slope of 0 here. Okay, let's not worry about tangent yet. We'll have a trig review in a little while. Okay, so what's next? Well, how about y equals square root of x? Well, we've been saying that this has a restricted domain. We've got 0, 0, 1, 1, and 4, 2. These are our reference points. Whereas with y equals cube root of x, that has an unrestricted domain. And so it looks like this. Hey, by the way, that's vertical. That's an undefined slope there. I don't want to do this kind of thing. That's not a vertical slope. So really try and make it vertical there, okay? We're going to be talking about slopes of lines a whole lot this year. And so now is a good time to start drawing these graphs accurately. Okay, this one passes through negative 1, negative 1. This one passes through 1, 1, and 0, 0. Remember, these are the same reference points for y equals x, but they're also the same reference points for y equals x to the third. Please don't draw the red graph when you're asked for the black one. I've got to know the shape as well as the reference points. Okay. What else do we have? Well, how about this one? Y equals square root r squared minus x squared. What's that going to look like? Well, if I had a plus and minus out in front, I could square both sides and add x squared to both sides, and hopefully you'd say, oh, that's the equation for a circle. And that's if I had a plus or minus in front. But if I don't have a plus and minus in front, then what I'm looking at is a semicircle. A semicircle. And my semicircle has negative r, positive r, 0, r as its reference points. And how about y equals 1 over x? We'll be talking a lot about rationals, but the most basic rational function is on our reference graph list. I've only got 2 points on this reference graph, 1, 1, and negative 1, negative 1. But please don't forget to draw and label the horizontal asymptote y equals 0 and the vertical asymptote x equals 0. Okay? We need to have these asymptotes labeled when we graph rational functions. Speaking about things that have asymptotes, what about y equals b to the x, where b is not equal to 0? So in this situation, we're talking about exponential functions like y equals 2 to the x, or y equals 3 to the x, or y equals 1/4 to the x. What do we know about these? Well, we know the reference points are -1, 1 over b, 0, 1, 1b, and we remember that all exponential functions have a horizontal asymptote at y equals 0 unless we do some transformations. So if I'm graphing y equals 2 to the x, my reference points will be -1, 1 over 2, 0, 1, 1, 2, with y equals 0, the horizontal asymptote. And it would be really good if you could graph this fast. Because you don't want to be spending your time on the calculus exam struggling to remember your pre-cal. That's what these first few weeks are all about, reminding you of all the sort of things that we need and helping you get more comfortable if you weren't as comfortable as you should be after last year. So that when we take on the calculus starting in Chapter 2, that you're much more comfortable and ready for it. Okay, the inverse of an exponential is a log function, log base b of x. And since this is the inverse, it passes through the inverse points, which means we flip all the exponential points. So instead of -1, 1 over b, we have 1 over b, -1. Instead of 0, 1, we have 1, 0. And instead of 1b, we have b, 1. Don't forget, since this is an inverse of an exponential has y equals 0 horizontal asymptote. That means that a log has x equals 0, a vertical asymptote. So if I have y equals log base 2 of x, then our graph has a vertical asymptote at 0 and passes through the points 1 over 2, -1, 1, 0, 2, 1, and don't forget the vertical asymptote. If you leave these points off, no credit. If you leave this off, you won't get credit. So please make sure that you have a complete graph, okay? All right, hey, what about this one? Y equals ln of x. Well, that's a log 2, and it has the same shape. It's got a vertical asymptote at 0, and the points are 1 over e, -1, 1, 0, and e1. Remember, ln of x is just log base e of x. Okay, so our base here is e. So those are our reference graphs. Those are the things that you need. Actually, I kind of want to throw in one more, but it's not really a reference graph because I can't quite apply my transformations to it. Remember, transformations only work on things that are functions. These are function transformations. And so if I had x squared plus y squared equals 4, I can't use my transformations on this because this isn't a function. This is a circle with a radius of 2. Fails the vertical line test, not a function. Can't use my transformations. But as we saw earlier, yeah, I can do a semicircle. I can do half of a circle. That's a function, so my transformations will work on that. Okay, now here's the other one that I think you should be more comfortable with. X equals y squared. So what's that look like? Well, it looks like a parabola that's fallen over. And it passes through 1, 1, 1, -1, and 0, 0. In fact, while we're talking about this one, we might also want to include absolute value of y. These will come up for us especially next semester. And so there's absolute value of y, actually passes through the same points. -1, and 0, 0. And if we try and do transformations of these, we get funky things happen. So if I see a -1 here, that shifts this graph down 1. But down 1 means down here. So then I have -1, 0, and I have 0, 1, and 0, -1 for my graph. Okay, so yeah, down. If I look at this graph sideways, if you look at it from over here, then it is down. But that's why, we won't be using transformations directly with this, but we will have to graph these. Okay, so what's next on the list to do? I'd like to visit piecewise functions for a moment. It's not uncommon that we run into a piecewise function in AP free response. So there's an expectation that we're comfortable not only evaluating piecewise functions, but also graphing piecewise functions. So let's start with this f of x. It comes in two pieces, square root of x minus 1 for x values greater than 1, and negative x squared plus 1 for x values less than or equal to 1. Okay, how do I do this? Well, remember, when it comes time for us to graph, we want to make two t-charts because we have two pieces. One for this piece with x values bigger than 1, 2 and 3, and one for this piece, negative x squared plus 1, for x values that are less than or equal to 1. So 1, 0, and negative 1. Now, the next thing is, it's very, very important, to put 1 there as well. How come? Well, because this is the break point. And what I don't know is, do these two pieces connect, or is there a jump discontinuity here? I know that x can't be 1, but it can go up to 1 and not include 1. Here, 1 is included. So I put a little closed circle to remind me of that, and an open circle to remind me that I want values bigger than 1. In fact, since this piece is square root of x minus 1, I'm actually going to use 5 here. How come? Because 5 minus 1 is 4, and the square root of 4 is 2. Square root of 2 minus 1 is 1, the square root of 1 is 1, and if I plug in a 1, I get the square root of 0, which is 0. So the first part of my graph, 1, 2, 3, 4, 5, 2. So we've got 5, 2, we've got 2, 1, and we have 1, 0. Remember, this is square root of x, and so I need that square root of x shape there. Don't forget to label the points on the graph. You may say, Mr. Kukla, but I have those points right over here. Why do I need to? I swear, I've asked kids to tell me where this is on the graph, and they point over here, they point over here. So I don't trust that just because you got those points there, that you know where they go over here. You have to show me and make sure that I know. Remember, this is AP Calculus. And AP Calculus isn't just learning about the calculus, it's learning how to communicate your knowledge of math to someone in Kansas City who's never met you and doesn't know how fabulous you are and how much you know. The only way they'll know those things is by what you write down. So please communicate effectively. Okay, so we've got this part here, the square root. Now what about this part? So for x values that are less than or equal to 1, I'm plugging in a 1, I'm getting 0, I'm plugging in a 0, I'm getting 1, I'm plugging in a negative 1, I'm getting 0. So note, this fills in that hole. Please, by all the gods, don't do that. Don't do that. You know what that communicates to that person in Kansas City? You don't know what the hell's going on there. You think there's a hole and a filled in simultaneously. Look, the hole was there because of this, but this filled the hole in. Please, no giant concentric circling. Just fill in the hole. Now what do we know? At 0, we have a value of 1, and at negative 1, we have a value of 0. We're down pointing for apple. Okay? Excellent. Now, what if instead of this, I had this? So that would change things over here. I plug in a 1, I get 3. I plug in a 0, I get 4. And I plug in a negative 1, and I get 3. So now our graph still has a hole here. But at 1, I have a closed circle at 3. At 0, 4, I have a point. And at negative 1, 3, I have a point. And we're down pointing for apple here. Okay? Closed circle, because I could be equal to, and open circle, because I just go up to 1. Now look, many of you wanted to start with 2. If you start with 2, this is your graph, and it's wrong. Why is it wrong? Because you left out all of these numbers between 1 and 2. There are an infinite number of numbers there. You left out an infinite amount of numbers from this graph. Of course it's going to be wrong. Okay, so that's graphing piecewise. What about evaluating? Let's go back to this function, and let's evaluate f of 1. So where do I plug this in? Do I plug it into both pieces? No. I have to think about this as an x value of 1. And I look over here at my domain restrictions and say x equals 1 with this piece. So I'm going to have negative 1 squared plus 1, which is negative 1 plus 1, or 0. F of 1 equals 0. Okay. What about f of 2? F of 2. Well, is 2 less than or equal to 1? No, so we're not going to plug it into this piece. But 2 is greater than 1, so we're going to plug it into the top piece and have 2 minus 1 square root of 1 over 1. Okay? And then if we have f of 0, 0 is less than 1, so I'm going to plug into that piece, and I get 1. All right. So we need to be able to graph and to evaluate piecewise functions. Why don't you show me you can with this one? F of x equals 3x plus 8 for x less than negative 2, x plus 1 squared for x's between negative 2 and 1, and the number 4 for x greater than or equal to 1. Oh, greater than. Can't have that. Oops. 4. Okay. So why don't you try graphing this and come back when you're done, or when you're stuck. Okay, welcome back. I got 3 pieces. I want 3 little t-charts. 3x plus 8 for x values less than negative 2. Negative 2 with an open circle. Negative 3, negative 4. I have this middle part that goes from negative 2, 0, 1. I want the endpoints and one other point, and 0 is pretty easy to put in there. And for x values greater than 1, I have 2 and 3, I've got 3. Plus 1 squared. Great. And wait, these are both closed circles. Okay, so let's get some values. If I plug a negative 2 in here, I get 2. If I plug a negative 3 in here, I have negative 1. And a negative 4 gives me a negative 4. How about over here? I plug in a negative 2. Negative 2 plus 1 is negative 1. Negative 1 squared is 1. I plug in a 0. I get 1. I plug in a 1, and I get 4. Now be careful, this is not horizontal line, this is parabola. Okay, if you plug in -1, you're going to have 0. So I need a parabola shape. But over here, no matter what x value I plug in, 3 petulantly says 3. So let's graph this piecewise function. So we've got -4, -4, -3, -1, and -2, 1 with an open, -2, 2 with an open circle. So -3, -1, -4, -4, and it's a linear equation. This next piece, -2, 1, with a closed circle, -1, 0, 0, 1, and 1, 4. And we stop there at 1, 4. This is 0, 1. This is -1, 0. And then finally, 3. So we have an open circle and 3, 3, 3. So we've got 2, 3, and 3, 3, and 4, 3. Okie doke. And what about evaluating this piecewise function? Are you comfortable with that? So what if I want to know f of 1? F of 1, does it go into this piece? No, it goes into this piece. 1 plus 1 is 2, 2 squared is 4. How about f of 4? Well, 4, no, not here, not here, oh yes, here, is 3. Okey-doke. All right, last thing I want to look at with you is going backwards. So I'm going to give you a graph and ask you to write the piecewise function for it. So my graph has a closed circle at 0, 1 and goes to 2, 0. And then from 2, 1 to 1, goes down to 5, 0. So how do we do this? Well, I have to write the equation for this line, and I know the slope here is down 1 and over 2, -1/2 x. And I know the y-intercept is 1. So this is going to work for x values from 0 to 2. Now I have to write this piece. Well, this one goes down 1 and not over 5. This is 2 to 5. This is 3 here. So down 1 over 3. Now, what about that y-intercept? Well, I don't know it. Here I was able to read this y-intercept off the graph. What I'm going to have to do is write the equation of this line. And oh my goodness, how often AP expects you to be really comfortable writing the equation of a line. So y minus 0 equals -1/3 x minus 5. So I get y equals -1/3 x plus 5/3. Okay, x plus 5/3. And that's going to work for x values that are greater than 2, not equal to, just greater than, and less than or equal to 5. Okie doke. There's our f of x. All right, so I did that one. Here's one for you. Please write the piecewise function for this graph. And this does line up. This is 1 here. Okay. Please write this piecewise function. Don't forget to pause the video while you do it. Okay, welcome back. So I've got this linear equation here. It goes up 1 and over 2, up 1 and over 2 with a y-intercept of 0. And that works from -2 to 0. This next piece goes down 3 and over 1, and that works from 0 to 1. And then finally we have this horizontal line, -3, for x values that are greater than 1. There's our f of x. Okie doke. Well, I hope this was a useful review for you. And remember, your homework assignment that goes with this is assignment 8. And assignment 8 is here. Don't worry, I'll scan these pages. SWAR, students will actively read. Yes, you should. And then do the problems. In fact, I recommend that you review all the notes you took. And oh my God, why are you not taking notes on these things? Take notes, read the pages, then do the homework. Every time. Piece of cake. All right. I will put that scan in our Office 365 team for you in Chapter 1 under Assignments, so you can get that PDF. Have fun and use GroupMe for questions or bring them up in our live Zoom sessions. Take care, everyone.